These are notes for Mel Ham's Math 60, City College of San Francisco, Monday, April the 6th. Section 7.4, page 626. We do a section a day. Tomorrow will be 7.5, Wednesday 7.6, Thursday 7.7, and then Friday the 10th will be the Chapter 7 exam, doing one section a day. As usual, if you find this print is too small, you should have the attachment that has all of this right with you. So ideally, rather than just looking at what I have over here, you can have this piece of paper right in front of you, full size. So as I point things out, you basically just listen to the audio and watching for what I'm pointing for, and you can look at your own paper, full size, of everything that I have here. And of course, I'm going faster than I normally would in class because this is a video. You can always fast forward or rewind as often as you wish. Problem 17, 2 radical 3 times radical 6. Again, I will say radical meaning the same thing as the square root. So the square root of 3 is the same thing as radical 3, but I'll say radical is a little bit easier to say, times radical 6. Now we can multiply a square root with a square root, but you can't multiply a number outside the radical with something that's inside the radical. So I can multiply radical 6 times radical 3, which is radical 18. So 2 radical 18. We're not done, however, because 18 contains a perfect square. 18 can be written as 9 times 2. And the reason why I want 9 times 2 and not, let's say, 6 times 3 is because 9 is a perfect square. So the next step, the square root of 9 will come outside and become 3. So I have 2 times 3, radical 2. 2 times 3 is 6, so 6 radical 2 is my answer. Notice I can multiply the 2 times the 3 since they're both outside the radical. I can multiply here the radical 3 times the radical 6. They're both inside the radical. But once I get to 6 radical 2, I leave it alone. Don't try to multiply these. You have one number that's outside and one number that's inside the radical, so just leave it alone. 21, similar idea, except they are cube roots. There's 3's here. So I can multiply these two together since they're both inside the radical. Cube root of 2 times the cube root of 12 is the cube root of 24. And now instead of taking out perfect squares, I want perfect cubes. Well, 24 is equal to 8 times 3. The reason why I want 8 is because 8 is a perfect cube. So, for instance, I don't want 4 times 6, for instance, because neither 4 nor 6 turn out to be perfect cubes. But 8 is a perfect cube. The perfect cube of 8 happens to be 2. So 2 comes outside, and stuck inside is the cube root of 3, and leave your answer like that. 25, we have fourth roots. So fourth root of 5a cubed, fourth root of 125a squared. I can multiply these two together. 5 times 125 is 625. A cubed times a squared is a to the 5th. And now a to the 5th I can rewrite as a to the 4th times a, because a to the 4th is a perfect fourth power. And it turns out the fourth root of 625 is a nice number. That's exactly 5. You may or may not memorize that, but it shouldn't be that hard to guess. After all, it ends with a 5, so since the number ends with a 5, you might guess 5. And lo and behold, if you do try 5 to the 4th power, 5 times 5 times 5 times 5, you do get 625. The fourth root of a to the 4th is just a, and we still have an a underneath the radical. So for my final answer, I have 5a times the fourth root of a. 29 is basically a distributive property. Radical 2 times 4 radical 6 plus 2 radical 7, we just distribute. Radical 2 times this, radical 2 times this. Again, we just multiply radical 2 times the radical 6, but don't try to combine it with the 4 being outside the radical. So radical 2 times radical 6 is radical 12. So temporarily I have 4 radical 12. Likewise here, if I take radical 2 times 2 radical 7, you can't do anything with the 2 being outside the radical, but radical 2 times radical 7 leaves me with a radical 14. So for now I have 4 radical 12 plus 2 radical 14. I can't do anything with radical 14. There's no perfect square besides 1 that I can take out of that. So for instance, you say 14 is 2 times 7. Well, that doesn't help because neither 2 nor 7 is a perfect square. However, 12, I can think of 12 as 4 times 3. So I rewrite 4 radical 12 as 4 radical 4 times 3, and then the next step, the square root of 4 will come outside and change to 2. Then I can multiply the 4 times the 2, giving me 8. So 8 radical 3 plus 2 radical 14 is my answer. Don't try to combine these anymore. These two radicals are unlike radicals, so we just leave it alone. 33 is the same kind of situation except they have cube roots, a little bit harder. So cube root of 2 times 4 times the cube root of 4 plus the cube root of 12. So leave this 4 alone, but cube root of 2 times the cube root of 4 is the cube root of 8. And the cube root of 2 times the cube root of 12, you can multiply the 2 times the 12, I have the cube root of 24. The cube root of 8 turns out to be 2, so I can write that as 4 times 2. The cube root of 24, well, I can write 24 as 8 times 3, and the reason why I want 8 again is because I can take the cube root of 8. In fact, I just did that over here. So write this as the cube root of 8 times 3. The cube root of 8 will come outside the next step as 2. So the final answer is 8 plus 2 times the cube root of 3. And coming back up here, 35. Radical 2 plus 1 times radical 2 minus 3. That looks like FOIL, first, outer, inner, last. So I can apply FOIL. First, radical 2 times radical 2 is just 2. Yes, you could say radical 2 times radical 2 is radical 4, but the square root of 4 is 2. But normally it's easier when you see something like this, the square root of 2 times the square root of 2, you can just go straight to saying that that's 2. Then outer radical 2 times negative 3 is negative 3 radical 2. You can't combine these. You have one number inside and one number outside, so you don't mix them. Inner, 1 radical 2 is just radical 2. And then last, 1 times a negative 3 is a negative 3. And 2 minus 3 is negative 1. These two middle terms are like, they're both radical 2's, so negative 3 radical 2 plus 1 radical 2 is negative 2 radical 2. Very similar to negative 3x plus x is equal to negative 2x. 39, similar, we're going to FOIL, except we have cube roots, so it's probably going to be a little bit harder. 2 times the cube root of 4 minus 3 times the cube root of 2 times 3 cube root of 4 plus 2 cube root of 10. So we FOIL first, that times that. I multiply outside by outside, 2 times 3 is 6. Multiply the inside times the inside, cube root of 4 times the cube root of 4 is the cube root of 16. Quick note again, this is the cube root of 16, not the square root of 16, so it doesn't simplify that easily. The square root of 16 is 4, but the cube root of 16 is not a nice number. We are going to do something with it. Okay, then outer, that times that. 2 times 2 is 4. Again, multiply the outside times the outside. Then multiply inside with the inside. Cube root of 4 times the cube root of 10 is the cube root of 40. Inner, this times this. Negative 3 times 3 is negative 9. Cube root of 2 times the cube root of 4 is the cube root of 8. And last, this times this. Negative 3 times 2 is negative 6. Combine outside with outside. And then inside with inside, cube root of 2 times the cube root of 10 is the cube root of 20. So here's my first, outer, inner, last. Now I take out perfect cubes if possible. 18 I can write as 8 times 2. And the reason why I want 8 times 2 again is because 8 is a perfect cube. Similarly, 40 I can write as 8 times 5. And the cube root of 8 already is 2. And this last one, cube root of 20, you can't do anything, so just leave that alone. Then over here, cube root of 8 is 2, so 6 times 2. Cube root of 2 is still inside. Similarly, over here, I've got the 4. Cube root of 8 becomes 2, that comes outside. Cube root of 5 is inside. Minus 9 times 2 is negative 18. That stays the same, 6 cube root of 20. And then we have 6 times 2 is 12, cube root of 2. 4 times 2 is 8, cube root of 5, minus 18, minus 6 cube root of 20. And we are done. There's nothing here that we can combine. These 4 terms are all unlike, so we leave it alone. 45, the cube root of 12 cube is just plain 12. I mean, if you almost just think of the definition, the cube root of 12 is the number by which if you were to cube it, you get back 12. 47, 3 radical 2 squared. Well, I square each item. I square the 3. 3 squared is 9. And square root of 2 squared is 2, for the same reason that cube root of 12 is cubed is equal to 12. The square root of 2 means the number such that when you square it, you get 2. So 9 times 2, which is 18. 51, 6 minus radical 3 squared. You could FOIL it by going 6 minus radical 3 times another 6 minus radical 3. I'm going to go ahead and use a shortcut that I showed you in class. It's based on a minus b squared. The shortcut is a squared minus 2ab plus b squared. So 6 is playing the role of a, radical 3 is playing the role of b. So I'm doing a squared, 6 squared is 36, minus 2ab, so minus 2 times 6, which is 12, times radical 3, so minus 12 radical 3, plus b squared, radical 3 squared is just 3. And I combine 36 plus 3, giving me 39, so 39 minus 12 radical 3. 57, we now have a set of problems where we're trying to rationalize the denominator. That means to get a nice denominator, not having a radical, but just a nice number like 3. So square root of 8 over 3, I can split it into 2, radical 8 over radical 3. For a problem like this, the best way to rationalize the denominator is to simply multiply by radical 3 over radical 3. You basically just copy this, because I know the radical 3 times radical 3 is just going to be regular 3. Yes, you could say radical 3 times radical 3 is radical 9, which ends up being 3, but it's a lot easier to just say whenever you have a radical 3 times radical 3, I just get 3. So the bottom is just 3, and that's what I have now, a rational denominator. For the numerator, the top, radical 8 times radical 3, they're both inside, so I can make that radical 24. And once again, I take out a perfect square. 24 I can write as 4 times 6. The reason why I want 4 times 6 is because 4 is a perfect square. That comes outside, becomes a 2. So 2 radical 6 over 3. 61, 1 over cube root of 2. I want to get a rational denominator. And so the object right now is, I say to myself, I would like this number to become an 8, because I like the cube root of 8. The cube root of 8 is 2. So knowing what I'm aiming for, I'm aiming to get a cube root of 8. I start off with a cube root of 2. That's why I'm multiplying by the cube root of 4 over the cube root of 4, because that will force me to have a cube root of 8 in the denominator. So 1 times that is just that. And now, just as we anticipated, cube root of 2 times the cube root of 4 is the cube root of 8. And no big surprise, I made it so that the cube root of 8 comes out nice to be 2. So I have a nice denominator, cube root of 4 divided by 2 is my answer. And coming up here, 69, square root of 48x squared over the square root of 8x squared y. We're allowed to put this all under one fraction. So the cube root of 48x squared over 8x squared y. The x squareds very conveniently cancel out. 48 divided by 8 is 6, so I have radical 6 over y, which is now very similar to 57. I split it into 2, radical 6 over radical y, and I just simply multiply the top and the bottom by radical y, because now radical y times radical y is just y. Again, you don't have to do the intermediate step of square root of y squared, which is going to be y, but you may if you want to, but it's sort of a waste of time. Whenever you see this situation, you can just go straight to y. And radical 6 times radical y, they're both underneath the radical, so radical 6y is my answer. So I leave it like so, and in case you're wondering, can I cancel this y with this y, the answer is no, because again, you don't mix up inside with outside. So this y is inside the radical, this is outside the radical, they cannot be combined or canceled in any way, shape, or form. 73, cube root of 4a to the 6 over cube root of 2a to the 5th b. Again, you can write the whole thing as one great big cube root. So I write the cube root of 4a to the 6th over 2a to the 5th b. 4 divided by 2 is 2. a to the 6th divided by a to the 5th is a to the 1, or just a. And I still have a b in the bottom. So I have the cube root of 2a over b. I split it into 2. And once again, the situation I'm at is I have the cube root of b. I would like the denominator to become b cubed, because the cube root of b cubed is just b. So I want there to be a b cubed. Right now it's just a b. So to force it to be a b cubed, I multiply by the cube root of b squared, top and bottom. So then I can combine these two, since they're both underneath the radical. The numerator is cube root of 2ab squared, and the bottom is now the cube root of b cubed, and the cube root of b cubed just becomes regular b. Again, I have a nice denominator, a rational denominator. This process is called rationalizing the denominator. I want to get a nice denominator here. So my final answer is the cube root of 2ab squared over b. And once again, don't try to cancel this b with this b, let's say, because this is inside the radical, this is outside the radical. They can't be combined. 81, the cube root of 4 over 81. You can't do anything with the cube root of 4, so I leave that alone. However, 81 is 27 times 3. And the reason why I want 27 is because 27 is a perfect cube. The cube root of 27 turns out to be 3. So I write this as the cube root of 4 over the cube root of 27 is just regular 3. And then I still have the cube root of 3. So at this stage of the game, I now have this and this. And once again, I'm playing the situation where I've got the cube root of 3. I want to build this up to 27 because the cube root of 27 is 3. So what do I multiply 3 by to get up to 27? Well, that would be 9. So I'll multiply the numerator and denominator by the cube root of 9, cube root of 9. So what that's going to do is force the denominator to be the cube root of 3 times 9, which is 27. And that's what I want because I know the cube root of 27, which is 3. And in the numerator at the top, I've got the cube root of 4 times 9 is 36. And then the cube root of 27 is 3. No big surprise. I made it that way. So that gives me 3 times 3. So the final answer is the cube root of 36 over 9. And no, we cannot do anything with the cube root of 36. It's not the square root of 36. The square root of 36 is 6. But the cube root of 36, you're saying what number cubed, what number times itself gives me 36. Well, it's not a nice number. You can get it on a calculator. And furthermore, there's no perfect cube, such as 8 or 27, that I can take out of this. So I leave that alone. 91 and 97, when you have a sum or a difference, you're adding or subtracting something, you want to multiply by something called the conjugate, which means to change the sign of what we have over here. So radical 2 over radical 5 plus 3, I want to multiply by radical 5 minus 3. Okay, so I change the sign. If this had been a minus, I would make this one into a plus. Because now this looks like something of the form a plus b, a minus b. These are called conjugates, C-O-N-G-U-G-A-T-E-S. You don't have to memorize that term, but just know what to do. Because that now looks like a plus b, a minus b. So when I multiply these conjugates, you might recall this comes out to be a squared minus b squared. In fact, we go backwards when we factor exactly. If we start off with the difference of two squares, a squared minus b squared, we know it can factorize into a plus b, a minus b. So once again, radical 5 plus 3, I multiply by radical 5 minus 3, which is called the conjugate of radical 5 plus 3. You just change the sign here. So now in the numerator, radical 2 times radical 5 is radical 10. Minus that times that, minus 3 radical 2 just stays minus 3 radical 2. We cannot combine something inside with something outside. Then the bottom is a squared minus b squared. So radical 5 squared is just 5. Again, you don't have to go radical 5 times radical 5 is radical 25, and then say, oh, radical 25 is 5. The shortcut is just to go straight to saying radical 5 times radical 5 is 5. Minus b squared, 3 squared is 9. And 5 minus 9 is negative 4. So radical 10 minus 3 radical 2 over negative 4 is an acceptable answer. If you look in the back of the book, they actually make it a little bit nicer. To have one less negative sign, the trick is to multiply the top and the bottom by negative 1. That forces the bottom to be a 4. And then if you notice, I have negative 1 times that is negative radical 10. And negative 3 radical 2 times negative 1 is positive 3 radical 2. I decided to put the positive first, so that's one less symbol. So the ultimate best answer is 3 radical 2 minus radical 10 over 4. Why is that considered better than this? Well, there's one less negative symbol. We don't like negative symbols. This entire expression has only one negative. This has two negatives, so this is considered a little bit cleaner. But I will let you leave it right over here. Finally, 97, something similar. Radical x minus radical y over radical x plus radical y. Once again, we multiply by the conjugate of the denominator. So radical x plus radical y, I want to multiply by radical x minus radical y. Top and bottom. If that had been a minus, I would multiply by the plus. And yes, indeed, it just so happens, I'm sure they made the problem that way, it happens that this thing is exactly the same as this, but no worry, just work it out anyway. So the bottom looks like a squared minus b squared, so radical x squared is just x, radical y squared is just y, so x minus y, I have a nice denominator. For the numerator, you can just FOIL. Radical x times radical x is x. Outer, that times that is negative radical xy. Inner is another negative radical xy. Last, negative radical y times negative radical y is positive y. And then these two combined, negative radical xy minus another radical xy is minus 2 radical xy. So final answer, x minus 2 radical xy plus y all over x minus y. So these are notes for Math 60, Monday, April the 6th, 7.4, page 626.